Hi everyone. My name is Ehsan Foroozanfard from Acconeer. I work as an antenna engineer at Acconeer, and this talk I will talk about the millimeter radar antenna simulation. So a little bit of introduction to the Acconeer pulse coherent radar. The radar system is based on the pulse coherent radar, which operates at 60 gigahertz frequency band, and the radar system delivers high precision and a low power consumption, and all the baseband RF front end and the antenna is included in a small package by a form factor of 5 by 5 millimeter. And a basic principle of this radar is that we send a very short pulses and then over the air, and then the reflected pulse from an object. We read that at the receiver side, and then we do read the radar data and do the processing in that. And on the left corner, we see one of our module, which the radar sensors integrated on a PCB. This module called XM112, high performance module, and then you can. There are also multiple communication interfaces that you can connect to the radar and read the data. For those who are interested, you're more than welcome to visit our website at acconeer.com. Moving to the more under the simulation domain, then I'll talk about the antenna in package simulation, which we do on a daily basis at Acconeer. So one example is the antenna in package designs, and the package type for this product is flip chip scale package, which consists of 4 layers stack up, and we have 2 antennas, one for transmitting and another one for the receiving. And the antenna types are folded dipole, which are operating from 57 to 64 gigahertz. And you can see on this slide that the chip is attached on the bottom side of the package. And then we have the ball grid array where we can read and write and communicate to the sensor. So in terms of environment in CST MWS Studio, specifically for design and simulation of the antenna package, we use time domain solver. I will talk about the main advantage of using a time domain solver for the pulse coherent radar. When we are designing a radar antenna, then there are multiple factors that the designer would consider for optimizing the antenna. One of them would be a radiation pattern of the antenna. Then we would like to optimize it, and then based on the requirement of the product. And then if there are more than one antennas, then the antenna mutual coupling could play an important role in the system performance. And also we do a lot of simulations to do the antenna matching to the RF, the transmitter and receiver chain. And another important factor for pulse coherent radar is the antenna fidelity, that we would like to minimize the impact of the antenna on the shape of the pulse that we are sending. And in time domain so well and transient analysis, that gives us the freedom to look at the performance in time and then extract the parameters we would like to analyze for the system studies. For example, if we have if you look at the antenna coupling between the transmitter and receiver, we can see how is the delay profile of the reflection, and then relate that to the radar range data, which could be very useful for system studies. Using CST MWave Studio gives us high confidence and designing the product, and also having an accurate simulation model also provide us a good confidence, and also saves time and costs in order to be able to make a fast iteration. And in this slide, you can see the comparison between simulated and measured radiation pattern of the radar pattern. On the left, you have the elevation cut, and on the right, you have the azimuth cut. And the blue curves shows the simulation result, and orange curves shows the measurement. And you can see they are in a very good agreement with each other, which shows how powerful the simulation tool can be for designing and verification of the design. And another type of application that we use CST MWave Studio is you're designing an external antenna for the radar. For example, some application we require to have an narrow beam width, and also increasing the gain, so be able to have the increased range for the radar. And here we see one example of dielectric lenses that we design for the radar sensor. On the left side, we have a picture of the Fresnel zone plated lens as an example. And on the right side, we have the lens on top of the sensor, which is placed on a holder, which holds the sensor itself and also the lens. As I mentioned, the main advantage of adding a lens then would be to narrow the beam width and also increase gain. So in this slide, you can see on the left side we have the radiation pattern of the sensor in the free space, and on the right side we have the radiation pattern where we added the FZP lens, and you can see that the radiation patterns is narrower, and then also the gain increased as well. So for designing dielectric lenses, one can use different simulation methods. So we can split that in two different approaches. One is using a full package model, where we have the full package, and then we use that to excite the dielectric lens. And then usually we go for a time domain solver in this case. And then the main advantage of this approach would be that we get all the detailed results that you need to consider. For example, you can get the near field coupling, you can have far field, you have the S parameters, and so on. But the disadvantage would be this would be a time consuming in terms of computational simulation computation. And another approach would be using a near field source. So to be able to do that, then once we do the simulation on the full model, and then export the near field source and also far field source. So we can use that near field source or far field source to do the lens design and optimization. And the main benefit of using this approach would to reduce the simulation time. So you get a much faster simulation results compared to the full model. And it's also useful so that you save a lot of time, and you would be useful if you need to do a lot of iteration to design a lens, for example. And to be able to build a confidence, and here made a comparison between the using a full model and near field source model. So on the left side, on the left figure, we have a box which represents a near field source. And then on top, we have a hyperbolic lens on top of that. And on the right figure, then we have a radiation pattern cut, where we use a full model source, which represents with a red curve, and then also the green curve shows the near field source. And as you can see, there are very good agreement with it, with each other, especially the main beam. And you can see on the back radiation, you have some differences there. This is because then that comes the difference between having a full model and near field source. So now we are increasing the scale of the problem, and then if you move one step further, then if you have a larger scale problem, like using a reflector for the radar. And in this case, the reflector would be much larger than a wavelength, and this using a full model and a time domain solver would take a lot of time to simulate this type of structure. So one way to optimize the simulation time would be to use asymptotic solvers. And the main benefit is using a geometric optics, which gives very fast results. And in this case, we have an example of parabolic reflector. And we use a near field source for excitation of this parabolic reflector. And then on the left side, we can see that also the rays, the optic rays, the incident rays with the blue lines, and then the reflected rays with the red color. This is a good way to check your design, to get a feedback of your design. And also on the right side, we can also get the far field pattern. So another type of problems we do a simulation on is the electromagnetic interference radiated simulations. And this is particularly interesting for us because when we are certifying the product, we need to pass a different certification, and on each country the regulation is different. So we need to check that the product is not violating any regulatory thresholds. And EMI is usually happens when there is an unwanted coupling from a source to a destination. So this could be in the shape of radiated or conducted emissions. And for this, it's quite important to have a very detailed model of the product. So in this case, we need to model the interface between the chip package and the PCB, and this involves a large and small scale detail of the chip package and PCB. And to be able to do that, we found the suitable solver to be the frequency domain solver, which can be suitable for this type of investigations. So by that, we come to the end of this talk, which can conclude by saying that in this talk cover a brief overview of various domains of EM simulation that we do on a daily basis at Acconeer, such as doing antenna package simulations, or external antenna for the radar, such as dielectric lens, reflectors, or characterizing of the radome for the radar, and also doing electromagnetic interference radiation investigations. Thank you for your time.